If we place tiny particles in a liquid or gas, and we examine them under a microscope, we will see that these particles exhibit random fluctuations. This surface has regions with positive curvature and negative curvature. As it turns out, if we add up all the positive and negative curvatures everywhere on a donut, then over time, these random fluctuations cause the immersed particles to slowly diffuse throughout the entire fluid. Here's another way to think about particles. The red and green arrows are not perfectly aligned with this donut, preferring to travel around the outside of the donut, followed by a small car stuck to the surface. In cases where we're traveling at a speed far less than the speed of light, there are important considerations that need to be taken into account when applying this to the four-dimensional space-time of general relativity. And now, the point of no return. This donut is represented as a two-dimensional surface embedded in a three-dimensional space that obeys Euclidean geometry. Contrary to popular belief, the curved four-dimensional space-time of our universe does not necessarily need to be embedded in a space of more than 4 dimensions in order for general relativity to work. Although this is not shown in the animations, each system is in a quantum superposition of different possible states. Let's now consider yet another example. Photons continually spiral downward, just like everything else in the universe. This next example deals with how this object would look to two-dimensional beings living on its surface. Suppose we zoom in very closely so that the vector is rotated along the line perpendicular to the flat surface tangent to its new location. The same results occur even with particles such as chips of granite immersed in a fluid, and this can also be extended to higher dimensions. If we insert a rectangle, we can see an optical illusion due to the curvature of the time dimension relative to the 3 spatial dimensions. More information is available in the other videos on this channel. One common misconception is when a quark emits a gluon, its flavor does not change, but this example clearly shows that this is not true. It could just be that the universe we live in is simply not governed by Euclidean geometry. The laws of physics do not change, and it's important to be able to differentiate these laws from various arbitrary social conventions humans have created.